Africa Arise Interactive. And the same work, would you like to learn computer programming? Let's learn. Tutorials for you to learn Africa Arise. Dream no small dreams and die empty. So welcome to the computer science class, and your teacher, your instructor is going to be Honest, and this is me over here on the screen. As you can see, I don't know why I designed it this way, but I just felt like, yeah, just put it like that. So this is the introduction to computer science, and we are talking computational thinking. And you may ask what this really means, computational thinking. But basically, for now, I just want you to take away the simple definition, which is thinking like a computer. For now, don't take it too big and try to think about a deeper definition of this. Just simply take it as thinking like a computer, thinking the way a computer approaches problem solving. Yeah, so for now, just take it as like that. And in this, we are going to talk about the basics and the foundational principles of computer. So computer science is all about problem solving. It's all about the inputs and the outputs. For example, we can give an example of your cell phone. When you look at your cell phone, it's all about the inputs and the outputs. If you are to think of your WhatsApp, you send a message, you are doing an input, and you are receiving a message, it's an output. So that is what it basically, that is what the foundational principles of computer science is basically. And what is computer science? What is computer science? So you can see from the screen is the inputs and outputs. Just think of a boiling jar. You put water in the jar, you boil your water, you pour the water in the kettle. But now, when you put the water from the kettle, pour the water from the kettle into the teapot, you are making tea. And when you pour the tea from the teapot into the cup, it now comes as what? As tea, which means you are solving a problem. There is a way, it involves or it entails problem solving. That's what computer science is all about. It's a way of solving problems, be they minor problems or complex problems. That is why we see simple mobile applications today, whereby you just use them to just take a photo. And we have got a very complex application which you can use to take photos. At the same time, you can use the same application for chatting, you can use the same application for video calling, and so forth. So the complexities are unlimited as long as a person can think on how to approach that particular problem solving. Yeah. Now, what kind of problem do we want to solve? How can we represent it? So before you think of solving any problem, First, you have to have the problem. What is the problem that you want to solve? And how can you represent it? So here is a simple example of the tiling system. I hope everybody who went for elementary school can remember this, whereby we used it to be taught how to count using our fingers. Your right hand has got 5 fingers, your left hand has got 5 fingers, your feet, both of your feet, right and left, they have got five fingers. So you'll be bunching together the two. You'll be bunching together all the fingers from your left, and they are 5, and all the fingers to your right are 5. You see, so if you take all of them, including the feet, you can have up to even 20. So this is one of the ways of representing data. It's one of the ways of representing data. And say, for instance, you don't have a bigger numbers, but you want to count big numbers, but you don't have. You can say, my left hand, instead of it, even if we have got 5 fingers, but instead of it representing 5 fingers, you can say, my left hand, the 5 fingers in my left hand, they represent hundreds or 1,000, and the 5 fingers in my right hand, they represent 1,000. And you say the same applies to your what? To your leg, to your feet, left and what? And right. In other words, you have a typical representation of data, whereby if we are to count all the fingers, we can say you have got 4,000. Why? Because one, the left hand has got a representation of 1,000, the right hand is a representation of 1,000, the left leg and the right leg, both of them, they have a representation of 1,000 and 1,000, and that will make 4,000. So think of this tally system, but how long now? How long can you count using fingers to represent data? Now there comes the question, because you want maybe to come to big numbers, like from 1,000 you go to tens of thousands, you want to go to hundreds of thousands, all the way to 1 million, 1 billion, trillion, quadrillion, and so forth. So how long will you keep representing data using your fingers? How do computers represent the information? That's how now, when we want to dive deeper and have an understanding of of solving complex problems. Now, that's where we come to have computer language. It is known also as machine language, which is simply called binary, zeros and ones. When a computer is switched off, is not running, it is 0. And when a computer is powered on, when you press that switch button on the computer, the on button, it's at 1. So binary is a number system whereby we only count 0 and 1. This is the computer or the machine language. In this regard, we are saying computers only understand one language. Zeros and ones is what computers know. This is amazing, isn't it? Because today we are able to do a lot of things using computers. We write texts, messages, writing in English, writing in different languages, French, Japanese, African languages, and so forth. We are writing them on computers, on our cell phones. But how is a computer able to understand these letters? And we even put all these big numbers, we write these big numbers, thousands, billions. How are computers able to understand these big numbers if they only know zeros and ones? It's a very good and valid question. It's a very good and valid question because if we say computers are so stupid to understand only zeros and ones, how do they manage to understand all these complex things? Now this leads us to another concept which computers use to understand what is happening, or for us to be able to use computers with all the things that we are using them in the world. So now, if computers are zeros and ones, how can they do anything useful? Definitely, you are tempted to think, or everyone is tempted to think, that they can't do anything, definitely, if they only understand zeros and ones. Now, the computer scientists, the very early computer scientists, are the ones who worked very, very hard to make computers do a lot of things that we are taking for granted today. If you are to look at the history of computer, the early computer scientists were working very hard to make sure that our lives today are better compared to their times. You will understand a lot as we go in this introductory module what was happening in those days. So now they formed a decimal representation of numbers. So we have to think decimal. Dec means 10. Dec means 10. So if we have got this number on the screen, as you can see, it's 123. 123. And on top of each number, you can see that there is, on top of 3, there is 1, and on top of 2, there is 10, and on top of 1, there is 100. This is a decimal representation of numbers. In other words, you see that 1 is simply 1, but 2 is representing 10, and 1, the first 1 to your right, to your left, represents 100. This is how decimal numbers work. So now, if you are to look at my numbers over here, down here, you see that we have managed to get 100 times 1 plus 10 times 2 and plus 1 times 3. We are multiplying each number by 1 and adding another number. We are multiplying each number by its value, So 100 is multiplied by 1 and 10 is multiplied by 2 and 3 is multiplied by 1. So in this sense, we have 100 plus 20 plus 3. When we abstract it down, we have 123. So this number is not a big number, but this is a simple way of making you understand that 123, within 123, we have 100, and we have 20, and we have 3. This is what it simply implies using the decimal place technique. So now we can move on, and if you are still if you are still younger, maybe you are at the age of 6, 7, or below 10, you may not understand some of these concepts. Maybe you are not doing them at school, but as time goes, just keep repeating these, and as time goes, you will get to understand what we really mean by this. And you can even skip and wait a little bit until we get to other tutorials whereby we are going to teach you to program in block in Scratch. This one is just intended to give a computer science background for people who have got questions regarding computer science and who want to know more about computer science, and so that when you begin to do computer programming using computer languages, you don't get that much intimidation because you know the background, where it is coming from and where it is going. Because I discovered that, like myself, the reason I was so afraid of computer science before I began, because I began it at later stage in my life at the age of 30 years. So I was I was having a very deep a feeling of intimidation because I never had access to such basics of computer science until I did my personal research. So for you to just start with a computer programming language without these such basics of understanding computer science, it may make you feel highly intimidated and you can easily give up, yet it is something that is worthy going for, is as far as today's world is concerned. Okay, so now here is a typical setup of the keyboard. How is it that we type letters and view images and edit videos then if computers only understand numbers, zeros and ones, decimal numbers? How is it that we are able to have these keyboards that will type all these? Typically, before I answer this question, we should note that we have two types of keyboards. The first one is this one which you are seeing. It's one of the regular keyboards that we are seeing today, that we are having today, but it was later on improved, and today we are using a better keyboard. As you can see on our cell phones, we are able to use emojis and much more on our keyboards, of which this first one doesn't have those functionalities. So this one was called the ASCII keyboard, American Standard for International Interchange. This is what it really it stands for. That's unlike us humans. Computers do not have numbers 0 to 10. Instead, zeros and ones. So we count 1, 2, 3, 10, up to 10, or up to 9, I mean. And from when we get to number 10, we begin to add some fixes going on. So we just say 9. On 9, we begin to add 1 plus 1 and 0, and 11, 1 and 1, 12, 1 and 2, 1 and 3, and so forth. But computers do not count that way. They count in zeros and ones only. So we are going to see zeros and ones, but however, is going to be in 1's place, 2's place, 4's place, etc., to represent each number under the hood. So in other words, what is happening here is when we get to 9, we begin to put 0, 1, 2, 3. And when you get to 19, we begin to change again. We take 2, 0, 3, you see, and we get to 29, we change, we go to 3, 0, 1, 2, 3. When you get to 40, to 39, we change, we put 4, 0, what, and so on. So if you are not getting this, simply understand that the computers, they just do the opposite of what we do. Instead of them adding as we do, they do kind of like subtracting, going backwards. That is why we have got 1's place, 2's place, 4's place, etc. to represent each number under the hood. Now, if this has been captured, now let's go to this system called abstraction. What computers are today, as you have seen them being improved as they are today, it's a formula called abstraction that was used. Think of building a house, constructing a house. When you are building a house, you start with the foundation. But you cannot live in a foundation. You want to improve the foundation. So when the foundation is laid and is fine, you begin to abstract, you begin to raise the structure to window level. Then you put windows, you abstract to the roof level, and you begin to put the roof, and you put the tiles or the iron sheets on top. You have improved it from the foundation, because you cannot say I have a house while at least you are having a foundation. You cannot live on a syllable foundation. So computers were improved since they started to what they are today using this method called abstraction. The computer scientists have been improving computers from the very simple concepts to these advanced concepts that they are today. That is why to learn computers today, for many of us, to learn computer science today is quite intimidating in the beginning, but later on it becomes so easy to understand. It is intimidating in the beginning because we are starting at a very high foundation. For us, if you are to trace going down to how it started with very, very, very simple concepts of just joining a switch on, off, on, and off. Why am I emphasizing on the switch of on and off? Computers is just a bunch of transistors, switches. Those, if you are to look at the green board, the motherboard of a computer, this one, and if you have been able to be introduced to a processor, computer processor, when you look at it, it is just a bunch of switches or transistors. Long back, the processor of a computer, today the processor of a computer is just very small. Some of them are even like your nail. But in those days when they were starting, they were almost or 2 times the size of that cup you used to drink coffee in. Imagine. And they had a bunch of switches. But I can even say the very first computers, one of the switches within their processors were even the size of the cup that you used to drink coffee in. That is to say, the processor itself was almost, I can say, a smaller bucket, like maybe 5 liters or even more than that. Okay. because the computers of those days were just like a big room, we can say a standard room size, where you can put a full bed and a wardrobe and so forth. Those were sizes of computers during that time. And they were abstracted. Through the process of abstracting, improving things now and again and making it smaller, but even making working better, that process was able to give us the computer that we have today, a computer like an iPad, a computer like an iPhone, a computer like an iPod for playing music. So imagine from a big house all the way to something that you can simply put in your pocket. These guys worked really hard to improve the computer system and the computer science for us to enjoy these things that we take for granted today. So we must appreciate the history of computer, and we must appreciate learning an introduction to computer science, because it brings us to a level of understanding that computers have come a long, long way. Now, let's talk about the example of abstraction. Now, let's look at the keyboard that we are using. The first keyboard was that has been used had 8 bits. 8 bits. The AXE keyboard uses 8 bits. American Standard Code for Information Interchange. 65 is the decimal number that represents capital letter A. This is an example of what? Of abstraction. So, in fact, what we are saying here is, when you are typing on the keyboard, the letter A, maybe your name is Aaron, or you want to say ask. So that first letter A in the word ask. On the keyboard, you are typing A, but under the hood, it's pressing a number. Which number is 65? Okay. But it doesn't end there. Then 66 is represented by the letter B, and the letter C under the hood is 67, and the letter D under the hood is what? 68. Why do we start at 65? A, B, C, D, E, F, G, H, I. Other numbers have been taken by the other symbols that we see on the keyboard. As you can see, if we are to go back on my keyboard over here, you can see that you've got symbols like escape, tab, caps, shift, and the Windows icon, alt, control, function, and these symbols like exclamation mark, tilde, and all these hashtag, $, percentage, and many more brackets and so forth. And all these ones, they also have the numbers that they are represented by under the hood. So in this example now, maybe you now begin to understand. We have about 256 possible values that we are seeing on the keyboard today. Let's have a look at the words. If you are typing on your phone, he to somebody, HI and exclamation mark, you are pressing under the hood the numbers 72, 73, and 33. Now you see the symbol for exclamation mark under the hood, it's represented by the number 33. But this one is decimal place. So, as we have said, the machine language, the computer language, the language that computers understands is called binary. Now, decimal is not the computer language, but it's a way of abstraction that was used in order to talk with the computer using the language that the computer understands. And now we come to letters, which is the language which we humans understands better. Although people can understand numbers, but it came to an understanding and evaluation that if we want to type emails, we cannot type the whole email communicating in numbers. We better understand letters than numbers. But computers are very, very good at working and understanding numbers. All right. So now, over here, now you are able to see that this abstraction that we have been talking about has taken the language which humans understand and make it understood by computers using abstraction. Now, what the numbers under the hood in machine language are these ones. The letter H is represented by the number 72, but the number 72 in binary is 1001000, and the number 73, which is a representation of the letter I, under the hood in binary, it's 1001001. And this is what happens each time you type anything that you are typing on your keyboard, on your computer, be it on your cell phone or what. Those emojis and so forth, they have the binary numbers, the zeros and ones structured this way that they are represented by, you see, in the decimal place rather. So going all the way to machine code, machine language, the zeros and ones. So now I hope you begin to get an understanding and the light is beginning to shine of what is really happening here. But what do we mean when we say the ASCII keyboard uses 8 bits? What is 8 bits? Bits is just an understanding of a storage of information, a representation of data. That is to say, 8 bits is an accumulation of a number of bytes. We are going to talk about that shortly, but for now, allow me to continue to talk about what we are having in place. Now, for now, let's wait for part 2, which we are going to give further examples of abstraction. So thank you for watching this one, and watch part 2 to continue with the computer science introduction course.